Hello learners, welcome to our mathematics lesson today. Today we are going to consider geometric progressions, and we are going to specifically look at how we can calculate the sum of geometric progressions. I'm Mr. Moses Mama to represent this lesson today. Now after the lesson, what should you be able to do? After this lesson, you should be able to calculate the sum of any given geometric series or a geometric progression. You should also be able to solve any problems related to geometric progressions. Now before we go any further, probably we consider briefly a few of the requisite knowledge that we are supposed to have at this point in time. Most of us probably know at this point in time what a geometric progression is. So, can we have anyone who can tell us what a geometric progression is? Or what type of a series or a progression is a geometric progression? Nancy?
Geometric progression is a sequence in which each term is formed by multiplying the previous term by constant amount.
Thank you so much. So that's very true, right? So for example, if the first term of the geometric progression is 2, if the first term of a geometric progression is 2, and then the constant that we are multiplying by this term is 3, what will be the next term? 6. What will be the next term?
18.
18. What will be the next term? 18 times 6, 8 times 3?
54.
54. 4. So this is a geometric progression. This is an example of a geometric progression. Okay? Yes. So a geometric progression, this term that we multiply constantly, what do we call it? This term we multiply constantly to get the next term, what do we call it? Yes, Margaret? It's a common ratio. So we call it the common ratio. So the constant number we multiply, constant number we multiply, we call it what? The common ratio. And most of the times we just denote it by R. We denote it by R. So now, how do we get the first term or the nth term of a GP? How can you get the nth term of a geometric progression? Fortunate?
By using a formula which is Tn
Tn
is equals to AR.
R.
And
That is the power.
Yes.
So the nth term of a geometric progression can be found using Tn equal to AR to the power n minus 1. Yes. So with this in mind now, we want to look at how we can get the sum of a geometric progression. For example, you are given this kind of a progression and then we tell you, find the sum of the first 10 terms of this geometric progression. How are we going to find it? Okay, we know the formula which I can give it to you without proof. But let me just show you how this formula was derived briefly, and then we look at the examples, okay?
Yes.
Good. We know that the sum of a geometric progression is given by Sn equal to A, open bracket, R to the power n minus 1, over R minus 1. Or A, 1 minus R to the power n, everything over 1 minus R. Right?
Yes.
So now how do we we come up with this? So we'll just show you how these formulas were derived, and then we'll use them to solve a few examples. Okay?
Yes.
Good. So we know for a geometric progression, the first term, what is the first term of a geometric progression? What letter do we usually use for the first term of a geometric progression? Okay. Yes, G. A. Good. So the first term is A.
Yes.
And then what will be the second term? What will be the second term according to our formula there? Let's try to substitute there. What will be the second term? Grace? The second term. Yes, Ernesto. Okay, remember we are multiplying by a constant number. We are multiplying by a constant what? Number. So this constant number, we said that we denote it by what? R. Okay, so then what will be the next term here? See over here?
R.
Yes, Miss.
Do A multiplied by R.
Okay.
Yes.
So it will be A times R plus A R squared plus A R
Cube.
power 3, plus, and also on and so forth, plus, then what will be the last term? What will be the last term? So the last term will be A R to the power n minus 1. We know that,
Yes.
Okay. Yeah. So the last term will be A R to the power n minus 1. Okay? So meaning that the term before that one will be what? The term before this. A R to the power n minus
0.
Aye. Yes. So it is always less one, You see? So it will be A plus AR plus AR squared plus AR to the power 3 plus going on and on and on. Okay? So now we are saying that this now is the sum. Right? Because we are adding these things, This is the sum. So now what we want is to come up with another equation which will give us the relationship of the two. So to do that, we will multiply this by R. So let's call this one equation 1. So once we do that, we are saying that now we multiply equation 1 by R throughout. So multiplying throughout equation 1 by R by S of n. R times S of n will be R Sn, and then equal to A times R AR times R AR times that one. And then it will follow the same way, plus, and then it will go on and on, plus. Now this one times R. This one times R. So we apply indices there. So when you apply indices there, what we are going to have is AR minus 1, n minus 1. When we apply indices, what do we do to indices when we are multiplying the numbers of the same base? What do we do to the powers? Yes.
We add the powers.
We add the powers. So when we add the power 1, which is R, will subtract here because we are adding. Yes. And then the final one, this one, will not have that minus 1, will simply be AR to the power A, right? How to get? When you just multiply through by R. So that's what we will get. Okay?
Yes.
Now, after doing this, yes, you have a question?
Yes, sir. Sir, I was kindly asking if you can repeat the words within A, R to the power n minus 2, how you came up with A, R to the power n minus 1.
Okay, so, okay, let me use that free space here. So, we are saying we have AR to the power n minus 2, right? And then we are saying we are multiplying this by what? R, right?
Yes.
We are multiplying this by R. So this R is to the power what? 1, eh?
Yes.
So let's see, ignore A for not really ignoring, but we are just going to consider those with the same bases we are multiplying there.
Yes.
So what are we going to do? It will be R n minus 2 this thing, eh? Right?
Yes.
And then we just use one base and then we subtract the powers, eh?
Yes.
Right?
Yes.
So doing so makes us now arrive at AR. Now this is n minus 2. We add the powers, eh? For multiplication. Plus 1. Right?
Yes.
So for multiplication we add the powers. So now we can work out this part, which is the negative 2 plus 1.
Negative 1.
Negative 1, which will bring us to AR n minus 1. So in a similar way, this one also, when we multiply by R is to the power 1. So negative 1, this one, plus the the 1 which is the power of R, the power negative 1 subtracts with the 1, and then we just remain with power n. Good. So we can continue, right?
Yes.
Okay. So this, let's go into equation 2. So now what we are going to do, since we have the two equations which are related, what we'll simply do now, we'll subtract them over there so that we don't erase this part. We subtract the two equations. So we are saying we are going to subtract equation 2 from equation 1.
Yes.
So subtracting equation 2 from equation 1 implies that we subtract this whole equation from that whole equation. Okay?
Yes.
Just the way we do it when we are solving some simultaneous equation, when we are subtracting those variables to solve a simultaneous equation. So subtracting this minus that, we have Sn minus Rsn, right?
Yes.
We are together?
Yes.
Which should give us, there's an equal sign there, should be equal to, and then now, from here, we'll see, we are subtracting these two equations, eh? But if you look at this equation and this equation, you can identify things that look the same. And what will happen to things that look the same when we are subtracting? They will subtract each other and give us z, right? So for example, this and this will subtract each other to give us a 0. That and that will subtract each other. That and that will subtract. And then here we'll have the a to the power, AR to the power 4 somewhere here.
Yes.
It will also go with that. You see?
Yes.
And then we'll continue doing the same for all terms until we reach at this term. This term first. After reaching this term, it will cancel with also the power n to the power 2. This one will also subtract with that one. Right?
Yes.
So what will just remain with will be a minus this. Eh?
Yes.
So what will just remain with will be a minus this. AR to the power n. So let's write it there now. So this is, it will be a minus a to the power n. A to R to the power n. Right?
Yes.
And then here we can factorize it and then simplify it, because basically we want to make Sn the subject of the
Formula.
So Sn 1 minus R equal to A 1 minus R. then we divide by 1 minus r, 1 minus r, and then we have Sn equal to a 1 minus r to the power n over 1 minus r as required. Yes. Okay. Yes. So we said that this can also be written as Sn equal to a r to the power n minus 1 over r minus 1. So these two equations are the same. Okay? These two equations are the same. The only thing is we are just encouraged to use this one when r is less than 1. Okay? We are encouraged to use this one when r is greater than 1. So, but whichever the case, when you use these formulas, they will still give you correct answers. They are the same. Okay? Yes. Good. We can now look at examples. Nice. So now let us consider some examples. Okay? So it says, example 1, find the sum of the first 10 terms, okay, of the geometric progression (1 over 8, 1 over 4, 1 over 2, and so on and so forth. Okay, so that's the progression. We are asked to find the sum. So what is the sum of the first 10 terms? There will be no need for you to start finding the other terms and then adding them at the end. No, we can simply use that formula that we've derived. Yes. So let's do solution here. So first of all, we can identify things that we need in order to find the sum of the first 10 terms. So first of all, we need to know what the first term is. Okay, what is the first term?
1 over 8.
1 over 8, this one here. And then what is r?
2.
How do we know? So, okay, someone to tell us how we find the value of r.
We're going to do T2 divided by T1.
Yeah, we can also do it T3 divided by T2, as long as you divide consecutive terms. Okay? Good. So we are going to put, so T2 in our case is 1 over 4. Over 1 over 8. Right?
Yes.
Yes. 1 over 4, 1 over 8, which is equal to 1 over 4 times
8 over 1.
Right?
Yes.
Good. And then this will give us 4 into 8, 2. 1. Yes. So we have to be careful here. Make sure we put the following term before the previous term. Right? Yes. Divide this like T2 divided by T1 or T3 divided by T2. So our R is 2. So now we can put this in the formula, which is Sn equal to A. So which R are we going to, which formula are we going to use?
The second one.
Rn minus 1. This one will be better to avoid negatives. Okay? But sometimes we get confused with some negatives. So we can use this one. And then S10 will be equal to, so A is 1 over 8. R is 2 power 10 minus 1 over 2 minus 1.
Yes.
Right?
Yes.
Yes. So working this one out, you can either use a calculator Or you can see from here that 2 minus 1 is 9. So you remain with just 1 over 8 here. And then 2 to the power 10 is what?
1,122.
And then minus 1?
1,023.
1,023. 0 to 3. And then you can multiply through there to give us some. What are we going to get?
127.875.
127.85 or 127.7 over 8. Out there? Yes. So this is going to be the sum of the first 10 terms of this progression. Any questions? No questions. Good. So now let's look at another example. Calculate correct to 3 significant figures. The sum of the first 8 terms of the GP 12, 8, then 5, 1 over 3. Okay? So similarly, what we are going to do, we identify those things we need to substitute in the formula. So we need the first term. What is the first term? 12. What is the second term? I mean the R. How do we find R again? 8 divided by this one or this divided by this. Yes. So automatically here we can see that it will be much easier using these first two. Yes. So it will be 8 divided by 12. Which gives us what? 2 over 3. Okay, good. So 2 over 3 is the R. So we do the same, we substitute there. Okay, the N is 8, first 8 terms. So we substitute in the formula. Looking at the R, which one will be the ideal formula to use? Sn equal to A1 R power N divided by 1. So this will give us A is what? 12. 1 minus, what is R? 2 over 3 to the power? 8 this time around, Okay. Right?
Yes.
Everything over 1 minus 2 over 3. Okay? So we can get our calculator working. Our calculator is working. Okay, so this one, we work out the denominator, it will be 2 over 3 power 8, and then the denominator 1 minus 2 over 3. 1 over 3, eh?
Yes.
1 over 3, and then working everything out now, using a calculator to 3 significant figures, you must be able to get 34.6, eh?
Yes.
Out again?
Yes.
Yes. So you should be able to get 34.6. So that's how we use the formula to calculate the sum of a given geometric progression. Yes.
So sir, if they haven't given us the first term, can we use the formula to find the first term?
Yes. Yes, but in most cases when they list them like that, then the very first term is our first term, right?
Yes.
Unless they tell us that it is starting from somewhere. Okay, we can still find the first term. And then we'll have to know what position this one is, eh?
Yes.
Memory.
Sir, is it possible to have R as 1?
No. It's not possible. We can't have a GP with R1. And then it will be a GP of 1 term, right?
Yes.
Margaret?
When writing the first term, or when you say you cannot write a decimal number.
The R. If it is a terminating decimal number, yes, it will help you. But usually we like using fractions because most of the times R can be expressed as a fraction like that. Yes. Sure. So now let's look at another example, which I'll give you a few seconds to do, and then you tell me the answer. Okay? So as I'm reading, make sure you are taking note of terms. Example, call it example 3, but it's your task to do. For example 3, if S7 of a GP is 6558 and the constant ratio is 3. Calculate the value of the first 10. If the sum of the first 7 terms of a GP is 6558 and the constant ratio is 3, calculate the value of the first 10. So basically you just have to use the formula. Yes. You are dear. What did you find? 6, eh? Yes. Can you come and show others how you did it? Yeah?
Yes.
You can come, please. Okay. You can even start from there, where you are.
So we're looking at geometric progression. We've been given a task here. We've not been given the first term, so we're supposed to find the first term. We get the formula which we've been given, which is sum of geometric progression equal to the first term, y, common ratio, the power n minus 1, over r minus 1. So since we're looking for the first term, and we've been given the sum of 7 numbers, the first 7 numbers is 6,558. So we use the same figure which we've been given, which is right here. Since we have not been given the first term, we just write AB. And the common ratio we've been given as 3. Then we subtract 1. Since the figure which we've been given for the sum of the first 7 numbers is 658, so we use the 7 as the power here. Over the common ratio, which is 3, subtract 1.
Okay, we can come and continue from here.
So, put the first term as A. So we do 3 to the power 7, we get
3 to the power 7, let's help her.
2,187. 2,187.
subtract 1. The first term, since we don't have it yet, we just put A. open bracket. When we do 3 to the power 7, we get 2,187. Then we subtract 1, close bracket, over 3 minus 1. Then, when we subtract 2,187 with 1, we get 2,186 over, when we subtract 1 from 3, we get 2. Then we cross multiply.
That's over 100.
So when we cross multiply, we get
13,116. 116.
Then we divide the same number so that we make A the subject of the formula. And we do the same number 2,186 over 2,186. Even this side. Six. That's it.
Thank you. So simply that's what we can do. So most of it, it's not always that they will give us a geometric progression and then they just say find the sum. No, we can be given any problem that is linked to sum of geometric progressions, and then we solve it accordingly. Do we have any questions as we reach the end of our lesson? Okay, so we have reached the end of our lesson today. I hope you enjoyed, and I hope you will be able to apply what we have learned in your studies. And from me, Moses Mama, and the TV crew, it's bye-bye for now. Until next time.